in celebration of a very special Asteroid Day. My name is William Gonzalez. I am with the FSI communications team, and I'm joined here by two very special people. I'm here with Luisa, Fernanda, Zambrano, Marin, and Sean Marshall, both of whom are from the University of Central Florida, Florida Space Institute researchers funded by NASA's Near Earth Object Observation Program. They have various years of research and observation experience dating back to their time as part of the Planetary Radar team in Arecibo. And they are here to talk about one thing and one thing only, and that is asteroids. This is how it's going to be working. I'm going to have a couple of talking points. You will just be able to talk to your knowledge about that, see if we can help answer some frequently asked questions. And then by the end, we will be addressing some very specific questions that we got through our social media. I will, however, start by asking, what is an asteroid?
So asteroids basically are rocks in space. When you look up at night, you can see stars, you can see planets. There's a whole bunch of smaller stuff close by that you can't see, so that's what we study. Those are asteroids. Some of them can come close to Earth, so those are the ones we really want to watch.
Adding to that a little bit, these rocks come in many shapes and forms and sizes. They sometimes come alone, or they come in pairs, or they come in triple systems. We've discovered that in the last decade, multiple systems that have more than two companions. So that is something very, very interesting. So like Sean said, these are rocks in space. And as I mentioned, these they come in different shapes. So in this slide, we can see that a potpourri of asteroids, some that are like really big, like Ceres is one of the first asteroids, the first asteroid discovered here on number 1 on the left. As I mentioned, sometimes they come in pairs, like 2001 SN263 that we can see on image number 2. We also have objects that are not as round, they're more like obloids, like Vesta, or even those that look like a peanut, number 7, Itokawa, which was the target of the Hayabusa mission.
Okay, that's really interesting and a nice overview of what asteroids are in general. I think that something that would help our audience a lot is maybe defining what an asteroid is not, because you see, there are a lot of people that get confused with different terms between asteroid and comet, and what's the difference between that and a meteor or a meteorite. If you could chime in on this.
Unlike the asteroids that are just dry rock, these comets have ices on them. Not like water ice from the fridge, but other types of ices. And they come into the inner part of the solar system, closer to the sun. Those ices, instead of melting and becoming like liquid, what happens with your ice, they go through a process called sublimation, where their ice instantaneously evaporates. So what we see is it's gas flowing out of the comets. And in this picture, you can see really cool, like two sides, like two tails. The comets not only have a gas line emanating in the direction of the sun, but the other one is kind of an electromagnetic line, like it's a plasma line that is of charged particles. And we can also see that, and they're just spectacular to look at. This is a beautiful set of images from the Rosetta mission to Comet 67P. All the outgassing that you see is because what I was explaining, the sunlight is hitting those ices and they're evaporating instantaneously. To me, these are just wonderful images. They're just so pretty to look at.
Yeah, and we should mention, historically, the difference between an asteroid and a comet was that the asteroid appears as just like a point of light. Asteroid means starlike, whereas comets, through even relatively simple telescopes, you could actually see some sort of like fuzz around them. So that's from material being boiled off as they get closer to the sun in the inner solar system. And so asteroids are mostly rocky, comets are more icy, and some objects are sort of right near the transition. It's not immediately obvious how we should classify them, but it makes things interesting for scientists.
Yes, and thinking back in time, right? When we didn't have all this knowledge about these rocks and how they were formed or what they were, comets were often associated with like catastrophic or doomsday events. When people will see like this, stars in the sky emanating comets, as was with eclipses too. These celestial events and objects in the celestial sphere, our lack of knowledge on what they were really had an impact on the cultures throughout history.
Even with all the knowledge that we have, we do still have some misinformation and some confusion around these topics. And it still begs the question, are they a danger to us? And what can we do about it? And what have we been doing about it?
Space is big. Please remember that. Earth is a relatively small target, but nevertheless, we do know that asteroids have hit Earth in the past and comets, and that could happen again in the future. So that's part of NASA's job. Keep an eye on them. Monitor the ones that are large and come close to Earth, like Luisa mentioned. Those are the ones that get prioritized for more detailed observations, and want to find all of them and nail down their orbits as accurately as we can possibly get them. That way, if there is one ever headed for Earth, we can plan a mission to deflect it.
Asteroids actually fall very often on Earth, meteors fall very often. But the ones that we really care about are the big ones, the ones that can actually create damage. We know of something called micrometeorites. These are like little tiny rocks that are like from 1 micrometer, 1 millimeter. We actually have specialized radars that are called meteorite radars that are focused on studying those. When they fall in, they just deposit their materials in the upper layers of the atmosphere. So that is the topic of a lot of high interest in studying, because we want to know how these can interact or affect our telecommunications. Now, but the ones that we really care about are objects that are larger, say, than 1 meter, 100 meters, or 10 kilometers. The 1 meters, if it falls in a populated area, right, depends on where it falls, it could create some impact, some damage. But objects that are greater than 100 meters, that could really, really create some damage. Having in mind that all of this depends on what the objects are made of. I don't know if you might remember several years ago, there was an asteroid that entered Russia, but because of its composition, when it came into the atmosphere, it exploded. So instead of just one rock landing, you had a ball that exploded, a rock that exploded in the atmosphere and produced a lot of smaller rocks that ended up falling in a city in Russia. But the objects that are greater than 100 meters or 10 kilometers, they're not that recurrent. We think they're about every 10,000 years or every 100 million years. We do have active sensors tracking, like the community. This is, for example, from CNEOS at NASA Jet Propulsion Laboratory. CNEOS is the Center for Near Earth Objects. And here, this plot is updated constantly. We can see the fireballs, meaning these asteroids that come into the atmosphere in some time, and we can see them glow. It's really important that we know that, there's organizations, there's groups that are actively working on this.
So you'll notice the largest marker there in red, that's the one that exploded over the city of Chelyabinsk in Russia in 2013.
Looking out up in the sky, we have a lot of space assets trying to find any objects that might come in. Actually, since 2008, we've been able to detect 8 objects before they actually made contact with Earth. This is an image of 2023 CX-1 that fell on the Netherlands, and we were able to track it a few hours before it landed. And not only instruments, we also have international collaborations focused on this. So, for example, the European Space Agency, the United Nations Office for Outer Space Affairs, NASA's Planetary Defense Coordination offices have all come together along with the International Asteroid Warning Network. And we do a practice exercise every 2 years that's called the Planetary Defense Conference, where we simulate a scenario of an asteroid impact. And here we have people from all over the world, from not only scientists, media, but emergency response agencies from many countries, to see what will be the strategies to be used. And actually, if you're interested in more information on these QR codes, you can see information about each one of these organizations. ESA has a European planetary defense plan in order. So does the NASA Planetary Defense Coordination Office. And they actually held a smaller tabletop exercise not long ago, and NASA broadcasted the summary of that meeting, where they simulated like a more precise object impact and how will be specifically the emergency response for such an event. So these objects don't come, the big ones that we care about are not that recurrent, so not to worry about. Also, we have a really, really vast network of people working and studying and just doing science related to discovering, characterizing, and following up on this potentially hazardous or potential impactor, or just any asteroid in general.
People who work on the asteroid surveys will tell you that if you want to prevent a future impact, the three most important things are find them early, and find them early. That way you have much more time to plan a response. So if we have decades to act, that's a lot easier than just having a couple of years to act. So some of the typical numbers here. So an orbital speed for an asteroid near the Earth is typically something like 30 kilometers per second. If you want to deflect it enough to miss Earth rather than hitting Earth, you only actually need to change the velocity by a couple of centimeters per second in the right direction at the right time. So, and one way that you can do this is literally just fly a spacecraft into the asteroid, and that will deflect it slightly. So this was tested a couple years ago with NASA's DART mission. DART is an acronym for Double Asteroid Redirect Test. So it hit Dimorphos, which is the little moon of the asteroid Didymos. So you can see them here, both here. So the target was to hit the little moon. So here are the images from DART just before the impact. So now you can see, so the primary is out of sight, and these are the final images as it crashed into the secondary. Just slowing down a little bit for the last few seconds here. And yeah, the final frame was only partially transmitted because the spacecraft crashed in the middle of sending that back. So the people who worked on this mission said they were never so happy to lose the signal from a spacecraft. But anyway, that worked well. So that's one asteroid, but it gives us confidence that this method works, and it did change the orbit of the little moon. So it gives us confidence that we can do this going forward.
So you have mentioned the different teams that are around the world and how they all collaborate to form this planetary defense team, basically. How exactly, though, do these instruments that you use for observation work? How is it the same as a normal telescope that we use, an optical telescope, or do you use a different kind of instrument?
So most asteroids are discovered by optical telescopes or some by infrared telescopes like NASA's WISE spacecraft, but basically they take an image of part of the sky, then go back a few hours later, look for something that moved. This is basically how Pluto was discovered. So astronomers took images of a certain part of the sky, went back, in that case, a few days later, looked for something that moved. So same basic principle, but the technology is quite a lot improved since then. So we can use computers, we can automate all of this, automatically pick out things that move. So that's how asteroids are discovered. But so Luisa and I do different types of observations.
Yes, we do. And on the discovery of asteroids, I wanted to add that, unlike stars, asteroids don't create their own light. Like, they don't emanate light. They reflect the light from the sun. Like, for example, the moon. The moon, we get to see it when the sun is illuminating the surface, and then the light that reflects back from the surface is seen by us here on Earth. For these optical telescopes, observatories, and surveys, they are discovered. They're hard to discover, right? That's why Sean said that, you look at one part of the sky and you see if things have changed, because the object needs to be passing by and the sunlight needs to be illuminating it at the right moment so we could actually see it. Otherwise, they're invisible. They're also in the thermal part, like Sean was mentioned. Snakes, they have infrared vision. So I don't know if you've seen also like those blue glasses that the Navy SEALs wear. They're like blue and you can see in the dark. Take that concept, say. So the light that is not the light that we can see, but the light, the heat that comes off your body, you're actually emanating light like at 100-watt light bulb right now. You just can't see it. But if you had thermal glasses, or if you were a snake, you could see the thermal footprint of the things around you. So these thermal telescopes are seeing not the visible light, but the heat that is emanating from these asteroids, and that helps us with characterizing them even further, because depending on their composition, they could get a little bit hotter, or they could have different thermal reflectance values. But besides optical and thermal, remember the electromagnetic spectrum. This is what light is, right? So we have the optical light, that is the one that we can see. We have thermal light, which is the heat, but we also have other parts of it, like for example, X-rays. If you ever get in a bone broken and you have to go to the doctor, they take a picture of you with a special beam of light that goes through your skin and can see on your bones. So it can penetrate the skin, but it reflects the light off the bone. So that way you can take a picture of your bones. So we can do that too with X-ray imaging with celestial objects. We can also do with the ultraviolet, which is other part of the electromagnetic spectrum, and see how they emanate. Asteroids are really not that visible on X-ray, but I just wanted to give you an example of parts of the electromagnetic spectrum, because we also have one more that we rarely talk about a lot, and that's radio. You know, when you're in your car and you're listening to the radio station and you can change the number of the station you're listening to, you can hear different radio station. That's because this radio wave, which is also an electromagnetic wave, it's transmitting in it, in the signal, the song that you're listening, and is being transmitted at specific frequency that your car can decode by tuning it to the right frequency. So we did something like that with the Arecibo radio telescope with planetary radar systems. There are other instruments in the world that do something similar, where we get radio waves and we can either send the radio wave or we can put a code on the wave, not a song, but a code. And then when we get the signal back, we can get information. That we got back can give us information about the object, but it gives us more information than optical, because on optical you can see the shape, you can see how it's rotating, but with radar we can get information on how fast it's moving and how precise it is at. Here we can see how RSC will work. This is how the planetary radar system works. So we transmitted a signal. You know, I gave you the example of your radio station and your music in the car. So instead of having a radio station transmitting from one place all throughout the world, we focused that signal, we transmitted it. It hits the surface of the asteroid, and the signal we get back, we can use it to get information about the object itself. Radar is really good for many things. This is a plot, little techie here, but it gives you an example on how we can know how fast the object is moving. We expect it to be moving at a certain velocity when it's at a certain place. And when we take the data, we can see if it's where we expected it or if it's not. If it's not, then it means that there has been a change in what the velocity with respect to who is looking at it is at. We can also do something called delayed Doppler imaging. This is where we actually put, say, a song code on the radar signal. And from that, we can get even more information. You know, we can get information of the time delay, like specifically to the order of meters in the distance. I mean, meters in an object that is like millions of meters away, it's really, really good resolution. And the same for velocity.
So this is an animation of, so on the left side is the simulated radar image, so Doppler shift, that's different frequencies along the horizontal axis, and then range, distance along the vertical axis increasing downwards. This is a binary. Right now the satellite is closer, and then the satellite starts to move back. So now they're the same distance. Then you'll see the satellite disappear when it goes behind the primary there. Okay, yeah, and Luisa, let's see, could you please show another slide where you have some of the actual radar images for a few asteroids? Yeah, great.
So here, for example, we have a radar image for 2014 JO25. As I mentioned earlier, these objects come in different shapes. Here, this type of objects, we call them contact binaries because it kind of looks like it's two objects that are gonna lump together. Or they could have been one object that lost a piece. We don't know. But what we do know is that we can have precise information on the rotation period and on the distance and the velocity that there are. We can also have information and characterize objects a little bit deeper. This is radar images from asteroid Phaethon. It's actually an asteroid that Sean has been working on and is the target of the Destiny Plus mission from the Japanese Space Agency. And this is the second largest PHA known. And once we have these images, the radar images, we can use computer software to create shape models of them. And these shape models that we can derive from radar data are really good quality for being a ground-based image. For example, this is the actual picture from a spacecraft image of asteroid Tutuatis. And on the left, you see the actual radar model. So they're pretty close. I mean, for being a ground base, like so far away, is pretty good resolution.
We like to say that radar is about the best you can do short of sending a spacecraft to the asteroid.
Yes, I yes.
And spacecraft missions cost hundreds of millions of dollars, and we only get one or two to an asteroid per decade. Whereas radar observations we can do from the ground for dozens of objects every year, get nice images like this, plus many other, a greater number of objects. We can't really get the detailed images, but we do get good measurements of their positions. That helps us nail down the object's orbit and make sure we know where it's going in the future.
And this radar is also very good for finding satellites. We can see, and we can definitely see if there's companion bodies. And sometimes you can create these really cool GIF animations where we can see how they're actually look to be moving. Or when we find more than two, like Florence. This was a really cool observation that we performed at Arecibo, and we found out this asteroid has two companions, which was also very, very interesting.
Thank you so much for this information on asteroids in general. I'm pretty sure a lot of the questions of the general audience have already been answered. However, we do have just a couple of very specific submitted questions that I would like to present, see how you tackle them. Okay. These were submitted to us by our followers in various social media platforms. And let's start with this. This one might hit a little bit close to home. It does come from one of the people that used to work there, but they have this question. With Arecibo out of the picture, how does planetary radar continue?
So Arecibo was the largest, most powerful, most sensitive planetary radar facility ever. So with Arecibo gone, unfortunately, that limits our capabilities somewhat. So the next best facility is Goldstone in California. It's part of NASA's Deep Space Network. So they can observe, they can see a larger fraction of the sky than Arecibo, but their transmitter is less powerful and the dish is smaller. So that means ultimately there's less objects they can get than Arecibo could get. So there's some things Arecibo could have seen that Goldstone can't see. And so we're trying to work and get a new and better replacement radar facility in the future. But for now, we are slightly limited. Goldstone has been ramping up their observations and trying to improve their system, but still it's hard to replace a 300-meter dish. So right now there is a bit of a loss there, and we're trying to restore it.
Is there anything you would like to add, Luisa?
No, I will start crying.
Oh, okay. For those that do not know, both Luisa and Sean worked various years at the Arecibo Observatory, where they were planetary radar professionals as part of the planetary radar team that used to do, I think, world record breaking observations in a year, or I recall.
So yeah, calendar year 2019, we got 126 objects, so more than any other radar facility could do or has done since. So we're proud of Arecibo's record.
Okay, maybe I will share something. So for the folks in here that don't know, this is what Arecibo looked like. It was a 305-meter single dish, and it had a platform that was hanging about 150 meters above the floor. So it was pretty big. I mean, if you look at this picture and the size of a car compared to everything else, it was a pretty big instrument. But not only
can you point out a car on that image?
Yes, right here's a car. Here's a car. It was not only impressive above, but also under the area under the deflector. When the telescope was created, they kind of imploded the mountain and had everything, it was just soil, gravel. And with time, the landscape was terraformed and it was filled with dwarf ferns and orchids. It was really beautiful. But the magic really happened because of this beautiful machine here. This is called the Klystron. It's pretty much like a electron gun, like imagine a light bulb, but that's really, really powerful. But instead of in opticals that you see the light, it's on radio, like we talked before. And this instrument that you see here was housed on the dome inside the platform. And I don't know about you guys, but I love watching unboxing videos. And a few in that same year telescope fell, we actually just got our new Klystron. And here's some pictures of our unboxing of the Klystron. We're all very excited because it was a custom made instrument and we waited a long time for it. And here you can see some of our unboxing pictures and our happy colleagues when we got it.
It's always very interesting to know how these large scale instruments work. We do have another question. This one's a little bit more specific on a certain asteroid called Apophis. Apparently, there are various people that are worried that we will be struck by this very large, from what I understand, asteroid, and that could lead into catastrophe. If you can please shed some light into this, what's actually going on?
Well, Apophis is going to come really, really close to Earth in 2029. And when we say close, remember, space is big, okay? But it means that it comes as close as where our satellites are in geosynchronous orbits. It's going to come between the Earth and the Moon orbit. So that's pretty close in terms of space. But it's not going to be coming like at the height of the International Space Station. Like it's going to come pretty close, but it's going to miss. It's going to miss. It's going to miss. But this subject is really interesting for the scientific community because instead of us having to send, say, missions like to Bennu that took several years, we have an object that's coming to the neighborhood. So we can just send, if we were going to be able to send several missions to study it as it comes close. Now, there has been studies on things that we don't know. It's how the asteroid is going to be affected by Earth's gravity, but we have several models that predict different things. But none of our models or the community's models are showing that Apophis is going to be of any threat to Earth in the next 100 years. NASA has also reformed the mission that went to Osiris, to the asteroid Bennu, the mission OSIRIS-REx, and now it's called mission OSIRIS-APEX. So they're gonna cleverly reuse the spacecraft that we use for Bennu, and once Apophis leaves the Earth's area, OSIRIS-APEX is going to meet with him and study it even more. And there's also initiatives from private companies and from other organizations to have missions go to Apophis and take advantage of this once of 1,000-year opportunity to study a near-Earth object that is coming into our neighborhood. But Apophis, it's going to miss the Earth. It's going to miss the Earth. It's going to miss the Earth. I'm going to say it 3 times so people remember. We have been having a workshop every year for the past 10 years since Apophis was discovered on the community that is interested in this. And we've had lots of optical observations, radar observations that we can really, really know and understand that Apophis is going to miss the Earth.
So Apophis was discovered in 2004. When it was first discovered, since we didn't have as much information about it, people realized pretty quickly there was a chance that it would hit the Earth in 2029. But now, again, with many more observations, so anytime we see one like that, you observe it with everything we've got. So now we know its orbit much more accurately. So we know it will come very close in 2029, but it's not going to hit. It's not going to hit. It's not going to hit. So it still comes close to the Earth on occasion. There will be a couple more close approaches, not as close later this century. So again, we'll keep an eye on it. We know it can't hit the Earth for at least 100 years, and we'll keep observing it and get more chances to push that horizon out further into the future. And again, we have at least a century of warning time if we ever need to do anything about that one, and most likely we won't. So.
And I like what Sean said. Once we know we hit it with everything we can. And it's really funny because this is a perfect example on how not only scientists are contributing to the body of science of planetary defense. Apophis was an object that was a subject to a worldwide citizen science campaign. So all of you amateur astronomers, backyard astronomers that are interested in this, you're welcome to help be part of, for example, the I1 network, where they do calls for observations of special objects like we did in Apophis. So we really did hit it with everything we had. We got a campaign where thousands of people all over the world in the last two operations were able to observe it, from using very small telescopes to using big telescopes, all of that, to really be able to get really, really precise information on the orbit, on the parameters, on all the things that we could about the object. So citizen science, I just wanted to add that here. It's really important. And they do give great contributions to our field, especially when we have observational campaigns like this.
I really like the emphasis, for the Apophis campaign, repeating it 3 times for emphasis. I really like that. I also like how the scientific community has banded together to pitch in for this. I like how you have turned what was originally thought to be possibly problematic event into an opportunity for research. Like, right, you're going to send the same spacecraft that studied Bennu up to it, and you're going to get more information out of it. That's actually really exciting. We do have the last 2 questions. One of them says, what kind of natural defenses does the Earth have against hazardous asteroids? And do we, in present day, have any ways to deflect or avoid an asteroid from hitting Earth? Then they say thank you.
So the biggest and best natural defense we have against asteroids is Jupiter. Jupiter is our best friend. Because most of many objects and when the planetary solar system was formed, got sucked in by the gravity of Jupiter. So many things fall on it because it has a bigger gravitational field.
One caveat there: Jupiter's a bit of a mixed bag, because it also can stir stuff up as well. But as far as natural defenses of Earth, I'd say, well, the best one is our atmosphere, actually. So that will break up the smaller objects. So smaller than about 20 meters, generally the object will break up in the Earth's atmosphere, like the upper atmosphere. So we mentioned the one that exploded over Chelyabinsk in Russia in 2013. So that exploded with the energy of like half a megaton of TNT, which is equivalent to a fairly large nuclear bomb. If that had happened near the surface, it would have been a catastrophe. But since it exploded in the upper atmosphere, the shockwave was somewhat damped out by the time it hit the ground. There were still about 1,000 people injured from that, mostly from broken glass. They saw the thing in the sky, then went to look, and the shockwave hit. So obviously, no one wants to get hit by a broken window, but the damage was not nearly as bad as it could have been if that explosion had happened right near the ground.
But Sean, if it breaks up, like if it makes the atmosphere defense plan is to break it up, isn't that worse?
Well, generally the one big one would do more damage than a bunch of small fragments. And again, the shockwave, since it started in the upper atmosphere, it was sort of damped out by the time it hit the ground. People were injured, but again, one was killed at least. So.
And how about the moon? Can the moon be considered to be a natural defense mechanism against asteroids?
Well, I guess stuff might occasionally hit the moon instead of the Earth, but again, space is big. Space is big is probably our best defense if you think of it that way.
That's a good one. Space is big. But man-made defenses, that kind of goes back to the second part of the question. Do we have any instruments, I guess? I think it was a question to defend. I know Sean touched earlier on DART, and that was the Double Asteroid Redirect mission. And that was kind of one of our first tests in space, like in situ tests, to see if we could actually pull off something like that. There's several deflection techniques in theory that have been developed. Like, for example, some people had said, what if you put a solar sail on the asteroid and then it will just fly away? Or what if you paint the surface of the asteroid with like black paint and it absorbs it and that pushes it away? I know, I like your face, William. It's like, what? It's like, but these are ideas, because we need out of the box ideas for great potential hazardous from great potential problems. But this idea of DART to hit it and change the orbit seems like a very logical one, right? Like you would think like that's the perfect one, but unless we tested it, we couldn't really know. Why? Because we're not hitting 2 billiard balls that are equally in the same mass, the same size, same density and all that. We're hitting a rock that's really big with probably something the size of a rice grain compared to the object. And what is the object made of? Like if it's made of something like what Sean said, that could break up in the atmosphere, what if when we hit it, we end up breaking it and then have a bigger problem? Or what if it's so rough, it's so solid that when we hit it, nothing would happen, right? We needed to know all of that, and DART gave us a lot of information from it. Actually, once the spacecraft hit, remember, DART didn't hit the main system. This was a binary system, and it hit the smaller one of it. Once it hit it, we saw there was a lot of debris flying out, and it was like a tail falling from it. So this object could be more of a rubble pile-like structure, and that will give us insight. Okay, what will be the limits of the explosion that it needs to have before it breaks up, or where should you hit it? How much change can you do to the orbit? So I think we have tested one method of deflection, which is, impacting it with something like a kinetic impactor on it. I know there's other, we've talked a bit about tethering, like, getting an asteroid and tethering it to something and then have it move with that. What other deflections techniques do you think of?
You can imagine other ones, but kinetic impactor is sort of our first choice. We know that works, and it works relatively quickly. Stuff like if you're painting the asteroid or trying to tether it or something, that might take a lot longer to make a bigger difference.
It's actually quite interesting. What I really like the most about your answer is the knowledge is going to help out the most, right? The more we know about this object, the sooner we know about it, that's actually the best way that we can know how to prepare for it, right? And there is one last question about a person that would like to know about a specific object. Actually, they're asking, they would like to hear more about SUSV, is what they are calling, and what is it likely to mate out of, and how close would it come to Earth?
I just quickly looked up asteroid Zusi. It looks like there are a few observations in different colors. So those observations suggest spectral type X, which means it might be metallic, maybe, but it seems like we don't have a lot of details on that. So stay tuned. Let's see. Hopefully we'll get another chance to observe it sometime soon.
If we can take anything away from this, is that this research is important. It's important to continue doing it, and it's important to have more information on asteroids, right? It is our best friend when it comes to this sort of defense for our planet. And I would like to thank you, Luisa. Thank you, Sean, very much for your time. To our audience, thank you for those who submitted questions. Thank you for those who has stayed curious about topics such as these, and follow pages such as these for more information. I will also have some links in the description so that you yourself can visit these databases and maybe read a little bit more about these asteroids, whichever you prefer. So thank you, and we'll catch you on the next one. Bye, guys.